All right, while I'm waiting for some of my other people to hopefully show up, somebody sent me email. Kelly, you sent me email. I screwed up the due date for the equilibrium homework. I did it when I was in the lab last night, and I clicked on the button that I thought was Thursday, and no, I put the wrong date on it. It was actually it's due tonight at midnight, because yeah, I screwed it up. I did, however, fix the missing couple of lines on how to do the calculations for the rate law lab. So I went back and fixed that bit so that it's a little bit more complete as far as telling you how to do all the different steps there. So that's been adjusted. I'm still kind of sort of behind on grading. I've got some lab stuff I haven't caught up on yet. But and also some people owe me things for lab too. So there's kind of a combination of things going on there. But yeah, I'm definitely missing several people. Are there questions about the equilibrium homework? As you hopefully finished it up over the, or tried to finish it up over the past couple of days, if you ran into snags about what the questions are asking for. And I'm also know that I'm behind on posting the lecture videos. One of my things to do this weekend is to make sure I get some of the ones that I have not yet downloaded, because you'd be surprised. It's like, if the internet's being speedy and cooperative, it takes like 11 minutes to download a lecture worth of video file. If the internet is being sluggish and uncooperative, sometimes it can take half an hour. And then since I load them through YouTube, that's another whole harangue too, that the uploading part is usually fairly fast, 5 minutes. But then it goes into this thing that it refers to as the processing phase. I have no idea what it does that processes it. That's beyond my tech skills. But sometimes it can take 6 hours before it tells me that it's done and viewable. So this is part of the reason why I'm behind. Part of it's my fault anyway, but I'm being kind of disorganized. But part of it is trying to deal with this lag thing that goes on when I download it from one system and then try to upload it to the other system so that I can post a usable link to it. Yeah, it kind of is a pain in the butt. All right, if there are no questions about general equilibrium, we're gonna talk some about acid-base equilibrium today then. I did get that uploaded. That's a file that's on the page in the Canvas shell that says notes by chapter. So I did actually get that tagged on or tacked onto the list of all the files there. So it should be there for you to download it / view it. All right. So I look for the right file. Oh, there's the right file. All right. So general equilibrium was not all that specific in terms of the what we were dealing with. We looked at some aqueous stuff. We looked at some gas equilibrium. We even touched a little bit on the heterogeneous equilibrium idea, where occasionally you have a solid and it's doesn't ultimately end up being written as part of your K expression. This chapter begins to move into specific applications, specific topics within equilibrium. So back in 111, we did some nomenclature, we did some acid-base reaction stuff to kind of rehash a little bit of that. In terms of what these two things are from a first semester point of view, if you drop it in water and it produces H plus ions, then we are going to indicate that that's what makes it an acid. From the first semester point of view, if you drop it in water and it makes OHs, we're going to say that that's what allows it to be a base. There is also a way to kind of generalize these this particular version of the explanations, and they are known as the Arrhenius definitions. So let me switch back over to my whiteboard for a moment so we can kind of go through just a little bit of rehash here. So things like HF, whoops, would help if I capitalize the F. Or for instance, H, and I can't do subscripts on here, but H2SO4, okay, or H3PO4, okay. All of these are things that we saw in first semester, and we went, starts with an H, it's not a water molecule, therefore we assume it's an acid. We saw things like sodium hydroxide, or cesium hydroxide. We also saw some that had more than one hydroxide present, like magnesium hydroxide. All of these are things that we dealt with, and we didn't really super categorize them as bases at the point, except in that when we did acid-base reactions, we said, gotta have something with an H, gotta have something with an OH. When you get them together, you have salt, and water. Salt being a general term, not necessarily specifically limited to sodium chloride. So these are things that we saw sort of general base level, basic level information from first semester. All right, let me switch back over to my other file. All right, as we are heading in deeper into equilibrium stuff, we're going to expand our definitions. Some of them will be, I'll call them inobvious or less obvious acids and bases, because this particular version of the theory is no longer the Arrhenius one. These are known as the Bronsted-Lowry model or the Bronsted-Lowry theory. So an acid is a proton donor. Okay, think about the wording there for a moment. A proton is a naked hydrogen, H+, and if it's giving it up or donating it to something else, that doesn't actually make it particularly different from the Arrhenius definition of what an acid is. But the expansion part begins to kind of come into play here. We talk about the base being a proton acceptor. So this time we're not specifying there are OHs involved. We are saying that you can take a molecule and tack an extra hydrogen on, and therefore call it a base. All right. My example here is probably less true than it should be. I should probably actually be using HF as opposed to HCl, but we're going to use it as kind of like our profile because it looks familiar. We've seen hydrochloric acid a lot before. Drop the hydrochloric acid in water. Because it actually interacts with the water molecule, you get H3O plus, which we have seen a little bit of before, goes by the name of hydronium, and you get a Cl minus. Okay, so think about this in terms of this expanded definition here. The HCl is an acid by any means of calling it an acid. It can be an acid because it kicks off a hydrogen, but it can also be an acid because it donates an H plus to something else. The water molecule, which you might not otherwise think of as a base, is now behaving like a base. It is accepting the hydrogen ion. And the fact that it does the accepting is what allows us to view it as a base. Like I said, this gives you extra ways to classify things as acids and bases. And when we're talking about acid-base reactivity, we then also have what we're going to refer to as conjugate acids and conjugate bases. They're basically the things that are on the product side of the reaction. Okay, you start with an acid and base, but you end up with a conjugate acid and a conjugate base because we're back to that whole goes both ways concept. Things on the right-hand side can, under equilibrium situations, flow backward toward the left, which does mean that sometimes they are going to do reactions that allow them to flow backwards. All right, look at the definitions for the conjugate versions. So the base, from a conjugate point of view, is whatever is left over after you ditch the hydrogen. So HCl, pluck off the hydrogen, you have a Cl minus left, which we are going to label as a conjugate base. The conjugate acid is the slightly bigger molecule that results after you add that hydrogen which fell off another molecule. They're always paired. So here are some more examples. There's also some additional ones in your textbook. Nitric acid. Once you pull off the hydrogen, the NO3 part of it, which is negatively charged, is a conjugate base because it's what's left over after you lost your hydrogen. You can take a hydroxide, which is a base by the Arrhenius definition, tack an extra hydrogen on it. You've actually created a water molecule now. But in terms of equilibrium, we can also consider that to be a conjugate base. All of these are all about competition. Your proton, does it want to live with the water molecule, or does it want to live with the whatever negatively charged half happened to be going on there? All of this is about that interplay between the two. So let me switch back over here to my whiteboard again. Let me pick on another acid molecule, and I'm going to specifically pick on one that has 2 hydrogens, because if I pick on oxalic acid, H2C2O4, there's my draw thing here, so I'm going to do, okay, let's go half and half, and switch back over here to text, and we've got H plus and HC2O4. Okay, think about that. I didn't disassemble my acid molecule all in one go, and that becomes more relevant later. But here I've got my H plus and my oxalate, or my bioxalate molecule here, which has a negative charge on it. If I want to be, however, be a little bit more truthful, I should probably actually write it this way. H2C2O4 plus water. Do my double-headed arrow here. And then over here on this side, it's not really a naked hydrogen. In actuality, it's an H3O plus and my bioxalate. Okay, that's more truthful. I can then label this one. Come on, I'm trying to get my draw thing to invoke here. All right, so this is acid. This one is behaving like a base. You will see water is very fickle, and we'll dwell on that more shortly. We've got then, okay, here's the water with its extra hydrogen attached to it. So we have conjugate acid. Okay, here's my missing a hydrogen. So this is conjugate base. Okay, and kind of think about this interplay back and forth here. Which side am I starting on? Am I losing H's or am I gaining H's? What's left over? So all of these play back and forth as we are heading through acid-base equilibrium. If you have a situation where water is the winner, okay, in the tug of war for who gets the hydrogen, if water is stronger, you will end up with your equilibrium, because remember, equilibrium is often tends to be toward the left or toward the right. Sometimes it's in the middle. This will give us an equilibrium where you have most of your products or most of your stuff is on the right-hand side. You get lots of products and not a lot of reactants left over. What if your A minus is stronger? And whatever was there that was negatively charged likes to steal a hydrogen from whatever is in there with it and regenerates your HA. That means your equilibrium is going to be very left, okay? Very much on the left. You're going to have lots of reactants and not a whole lot of products. All right. New letters of the alphabet to put below our K. We had KCs and KPs in the last chapter. Beginning here of this chapter, we're going to toss another one in. We're going to have KAs. Now, it kind of vaguely looks like it's missing something because I have two things on the top and I only have one thing on the bottom. Water in and of itself, H2O, is usually not written in equilibrium expressions. It is considered to be, because remember, think about your calculation back from lab where it says find the molarity of pure water. And we determined that pure water is around 55 molar. These reactions that are happening with acids and bases are not going to dramatically change the concentration of your water itself. Therefore, it's usually considered to be an unchanging value. So we have ionized pieces on the top. And yes, I shorthanded this, okay? Because you will see, and even the textbook is sort of guilty of this to some degree. Instead of writing H3O plus every time, they often shortcut it and just write it H plus. Yes, in reality, it's an H3O plus molecule, but it tends to get shorthanded this way. So let me hop back to my whiteboard again. What we're doing is we are looking at okay, this is your, we'll call this just sort of your generic equation. HA plus water. If I actually use the right letters of the alphabet on this. All right. And we'll put our equilibrium symbol in here. And then we'll go over here. And text. And we'll do H3O plus. Oops. H3O plus and A minus. Okay. This is the shows everything molecule, or the shows everything reaction. Okay. The shorthand version. Okay. We're going to go over here and go HA. Text. HA. All right. Draw my equilibrium in. And then do H plus and A minus. Oops. Capital A would be helpful. All right. They actually both mean the same thing. Okay. One of them is kind of the cryptic shorthand. It doesn't show the water. It also doesn't show the water within the H3O plus molecule. Or it's like, it's a way of kind of just dealing with the parts that are active. So, and I have a really big tendency to use this kind of second version here. But your textbook also talks a little bit about why or how it's shorthanded this way. All right, back to note stuff. HA is the one that hasn't fallen apart yet. H plus and A minus are the two pieces. Ka has a name. Ka is called the acid dissociation constant. It is something with a negative exponent. You will never see Ka values with positive exponents. Other Ks, yes, maybe. Not Kas or Kbs. So I'm going to pick on the most stereotypical, everybody picks on this molecule, which is acetic acid. Acetic acid is a not very powerful acid. It's vinegar. I can write my equilibrium expression, Ka, and then put the two pieces, the H plus and the acetate part, on the top. And then I put the part that is not ionized, the whole fully assembled molecule, on the bottom. Which kind of comes back to, what do we mean when we talk about strong acids? What do we mean when we talk about weak acids? Despite what you might think, strength has nothing to do with concentration. Strength has to do with ionization, also sometimes known as dissociation. Dissociation means to fall apart when you're talking about chemistry. So a strong acid falls apart pretty much 100%. When it says the equilibrium lies far to the right, it means you get lots of plus and minus pieces, and almost none of it stays stuck together as H whatever, A being the generic letter that's used. If you want to calculate percent ionization, you put the ionized concentration on the top, you put your starting concentration, also referred to as initial concentration, on the bottom, do your division, and since it is a percentage, multiply by 100 before you're done. There are 4 acids, which are always considered to be strong acids, no matter what concentration they are in: hydrochloric, sulfuric, nitric, and the bottom one is probably less familiar. You probably saw it in passing when the nomenclature sections were done. HClO4, known as perchloric acid. Perchloric acid falls apart pretty much 100%. It also is used relatively extensively for doing DNA work. If you want to unzip some DNA and put some other pieces in and zip it back up and add a few restriction endonucleases and tinker along with the code and all of that, perchloric acid is one of the things that you use to help facilitate that. So let's go back to looking at HCl again. HCl, not a weak acid, is, if you had 100 molecules of it, you drop it in water, at least 99, maybe all 100, are going to do that hydrogen swap. The hydrogen is going to fall off and go to live with the water molecule and leave you a Cl- as the anion part, the conjugate base part. And it's pretty much a perfect scenario in that pretty much every single one, or close to every single one, is going to actually fall apart. Strong acids yield really wimpy conjugate bases. So that Cl-, its ability to go back and steal a proton from somebody else is minimal. It is so hard to get the chloride to go do that sort of thing. Weak acids usually mean an awful lot of the HA, the acid with the hydrogen still attached, actually stays that way. It stays in such a scenario of having the HA and not giving you H pluses and A minuses. We say that the equilibrium is to the left because lots of reactants, only a little products. Hydrofluoric acid is a weak acid. If you look up some values for this, you will find out that hydrofluoric, for as evil as it is, and believe me, it is a truly evil acid, only ionizes about 8.4%. You're going to get lots of HA, and of course there's water in there because it's an aqueous solution. You're not going to get a lot of H3O plus and A minus. Actually, if I go back and kind of amend this a little bit to kind of show you more what we're looking at, HF plus the water molecule gives you, oops, use my equal sign there. So H3 O O plus, and then my A minus, which in this case is not an A, it's an F. F minus. You have lots of reactants, not hardly any products. So let me talk about hydrofluoric acid for just a moment because it's sort of relevant. So hydrofluoric acid is the one that they use for etching glass, which also means that you cannot store it in a glass bottle. They are typically stored in a Nalgene bottle, Nalgene being that nice, somewhat flexible plastic like squeeze bottles are made out of in the lab. But because hydrofluoric acid is capable of etching glass and not able to be stored in glass, it also makes it really dangerous. Hydrofluoric acid, if you have the misfortune to get it on your skin, basically eats until it hits bone because it will not stop dissociating until it reacts with calcium. So people who work with hydrofluoric acid for the purpose of etching glass usually keep a bottle of calcium hydroxide nearby for neutralizing it in case there's a spill. I have a friend who lives on the West Coast who started out his career as an environmental chemist, and he was doing X-ray crystallography, which involves dissolving various crystalline salts in hydrofluoric acid and then recrystallizing them so that you get a better crystal for putting into the machine. And he cracked a container of hydrofluoric acid at one point. And as you hopefully have noticed, our lab has a shower in it. Pretty much all good chemistry labs contain a safety shower. So when he cracked the bottle and it dribbled, his comment, when I talked to him at a later point in time, he's like, I have never been naked so fast in my life, because he wanted to make sure that whatever of the hydrofluoric acid hit his clothes didn't actually soak through and make it to skin. So yeah, he like stripped and washed it all off to get it off as fast as possible. So we keep seeing water. Water does all sorts of things on both sides of the equation when we're talking about acids and bases. Water is sometimes referred to as amphoprotic. You might also see the term amphoteric. Both of them basically mean the same thing. Water's fickle. It can behave like an acid if you put it with a base. It can behave like a base if you put it with an acid. So water has lots of flexibility in its behavior. So to kind of sum up some of the generalizations that underlie this chapter. If you have a strong acid, in comparison, it will have a large Ka value. It will have equilibrium that is mostly on the right. Lots of products, very few reactants, which then also means you will have lots of H pluses, which remember is the shorthand version of H3O plus. If you have a weak acid, you are going to have little Kas. You're also going to have equilibrium that is mostly to the left. Lots of reactants, not too very many products, which therefore means you have a lot of HA, again, A being your generic whatever stuck to the hydrogen, not a lot of products. So we can make some generalizations there that kind of help us categorize whether an acid should be considered strong or whether an acid should be considered weak. Some more terminology, some of which has been touched on in the past. Monoprotic, one hydrogen, one acidic proton, if we're talking Bronsted-Lowry theory. So HCl, nitric, pretty much all the carboxylic acids that we were looking at the beginning of the semester, the overwhelming majority of those are monoprotic. And there's a few that are diprotic. Diprotic is two hydrogens you could lose. Sulfuric acid, the one I was doing on the whiteboard, H2C2O4, which is oxalic acid, that one's diprotic. Triprotics are kind of rare. It is not that they don't exist, they do, but there's definitely not as many of them. The one that you see the most of in general chemistry is phosphoric. If you go on to take later semesters of more organic than the little bit that we covered at the beginning of the semester, you will see some additional acids that are capable of losing 3 hydrogens. A couple more terms here. Oxyacids, because there are some that aren't, okay? Anything that contains oxygen atoms. What wouldn't be an oxyacid? Hydrochloric, hydrofluoric, hydrobromic, hydrocyanic, HCN. All of those would not be oxyacids, but a lot of the ones that we deal with are. They usually have a polyatomic attached to them. Nitrate, phosphate, sulfate, sulfite. We can also, as opposed to calling them carboxylic acids, you also might see them referred to more generically as organic acids. Again, back to what we were looking at the beginning of the chapter, beginning of the semester. Formic acid, single carbon. It's got one dangling hydrogen on one side, but then it's got the OH on the right-hand side there. That's actually the side where the hydrogen gets lost from. It does not get lost from the left side. For acetic acid, again, it's the hydrogen that is dangling out past the oxygen atom that is the one that is lost. So as we're dealing with all of these things that have water as a part of their reaction, and we know water is fickle and can do this gain or lose thing, you begin to embrace the idea that what if it happened to steal from itself? Not impossible. You can get two water molecules to snuggle up next to each other, and a small portion of them, not many, will swipe a hydrogen from its buddy, and you get H3O plus and OH minus. They refer to this as auto ionization. Auto meaning self, like in like autobiography. So it does happen. Now, granted, it's not a super aggressive reaction. Note here it says equilibrium lies far to the left. If you actually start looking at what kind of ratios are we actually talking about? If you had 1 billion molecules of water, distilled water, all by themselves in a beaker, 2 out of every billion would do this. So it's not real popular, okay? But it does happen. You will sometimes see this particular, I actually don't know why my H2O with the square duplicated. For some reason, it's on there twice. I think that's because of the way I broke the page. You will sometimes see this actually written as, I'm going to put it in there for right at the moment, K prime. Okay, actually, oh, that was weird. Okay, let me go back up and push this down a little bit further so that it looks like it's all in one place. Makes it easier to read. All right, so K prime, because remember when we saw primes briefly in the last chapter, we said it's often a way of writing a temporary version before you get to the end. So we have our 2 ionized pieces on the top. We have our H2O squared on the bottom, but it's really not, you don't usually see it in that form. This again, I'm running into this problem of there's usually stuff I write all over the board that I did not add. So let me go back and add this in. All right, I'm going to do KW equals, and we're only going to copy the top half of this because the bottom goes away. Oops. Let me do this in such a way that it retains my upscripts. There. Okay. All right. So water, pure, actual water, not ionized, not with a plus, not with a minus, goes away. Okay. And more letters of the alphabet. We now have more than just Ka. Now we have Kw. It also has a name. We're going to call it the ionization constant for water. And unlike Kas, which have a wide variety of possibilities as long as they're negative exponents, Kw has a fixed value. Kw is 1 times 10 to the negative 14th. There are no units. It is a value that gets used repeatedly to help find other information in terms of H pluses and OH minuses. All right. If you have pure water, which has that value of 1 times 10 to the negative 14th, there's nothing else present, you basically divide it in half, divide it by itself, so that your H plus and your OH minus are the same value. they both end up being 1 times 10 to the negative 7th. Because if you multiply them back together, you get your kW back, 1 times 10 to the negative 14th. We can also head towards some generalizations here. If they're equal to each other, my solution is neutral. If my H plus is a greater concentration than my OH minus, then we're acidic. What if I flipped it? What if my OH is bigger than my H plus? Then we're basic. In a little way, it's like a seesaw. If you push up, or push down rather, on one of those two items, the other one goes up in response, okay? Unless your seesaw is broken, if you sit on one end, the other end goes up, okay? So if I increase my H plus, it will decrease my OH minus, and flip. If my OH minus increases, my H plus will decrease. They do not vary independent of each other in the same equation. So the last thing we're going to kind of deal with tonight, and because we're coming up on spring break and I'm missing a lot of people tonight, I'm going to kind of not get too much deeper into this. Let me do one or two last examples here. Look at your equation in terms of the rearrange there. If you want to find OH minus, it's Kw over H plus. So what if my H plus was 1 to the negative 4th? Put it in to the equation, put the 1 to the negative 14th on the top, put the 1 to the negative 4th on the bottom, do your division. My hydroxide concentration is to the negative 10th. And it fits the criteria of H plus is bigger than OH minus, therefore it is an acidic solution. What if I go in the opposite direction? What if I say my OH minus is 0.00037, 3.7 times 10 to the negative 4th? Again, put your Kw on the top, put your given value in the bottom, 0.0037. Finish your division. I've got 2.7 times 10 to the negative 11th. Again, think about your comparison. I actually have relatively larger amount of OH than I have of H plus. Therefore, it is a basic solution. So this gives you a introduction to what's the difference between Arrhenius acids and bases versus the Bronsted-Lowry ones. There's yet a third version which comes at the end of the chapter. It gives you the concept of water is a big piece of this. Water helps you trade your hydrogen around. We have KWs and KAs. KBs are coming. You can use the KW equation to find the other part once you know 1/2. We're going to head into, post-spring break, we are going to head into pHs, POHs, pKas and PKBs, KBs, and some other things are coming up later in this chapter. So things to keep in mind. Hopefully sometime before midnight tonight, turn in your homework for the equilibrium, and then post-spring break, I will go over that. You will end up with test 2 probably the Thursday, basically the weekend after we get back from spring break. So kind of pencil that in, as that is almost cast in stone. Okay. I hesitate to say anything like is absolutely like a dead, certainty, because I did things like that last year at exactly this time, and then the universe exploded. So I kind of hesitate to go, oh yes, we're going to do it this way. Because yeah, last spring break was chaos of orders of magnitude that I never comprehended. Which now seems like it's 1 year ago, and we all look back to the before times, and it just seems like it's been a huge amount of time. I think because we're all doing life differently. Questions about homework for tonight or this bit of the acid-base home or acid-base equilibrium stuff? Like I said, I will do my best to catch up on posting the video links over spring break. I got to get them all downloaded and re-uploaded again so that they have YouTube links for them. If you owe me lab stuff, work on that. Turn it into me digitally if possible over spring break. Get caught up because you only have 7 weeks when we come back. I think it is 7 or 8. We're just about halfway through right now. So you still have half a semester, but you only have half a semester. And some people owe me things. Questions? Otherwise, I will see you Tuesday after break. So a week and a half from now. Bye.